would the world look like with a computer that could accurately model the laws of nature? That's the promise of quantum computing. But there have always been limitations. It will solve problems unsolvable by the combined power of all the world's compute today.
For nearly 2 decades, the Microsoft Quantum Project poured hundreds of millions of dollars into one of the most secretive scientific gambles in modern history, hidden inside a nondescript building on a university campus in the Netherlands, chasing a particle that had never been confirmed to exist, and a machine that would have rewritten the rules of encryption, intelligence, and warfare.
The challenge is qubits are actually pretty delicate in general, so you need underlying qubits that are really stable. But you don't want that to come at a cost, because you don't want your underlying qubits to be really big. That's one way to make them more stable, is have them really big.
Then, without warning, the Microsoft Quantum Project went dark. The lab equipment was unplugged, the collaborators scattered, the papers vanished from the public record. And the official explanation Microsoft has offered in the 4 years since is so thin that not a single physicist outside that building is willing to repeat it with a straight face. What they were actually building. Before we get into what disappeared from that building, you need to understand what they were trying to make, because almost every explanation of quantum computing you have ever seen is terrible. A presenter stands in front of a glowing blue animation, says a quantum computer can be a 1 and a 0 at the same time, then stares into the camera like they just explained the universe. They explain nothing. Try this instead. The device you are watching this on works in bits. Every piece of information is a 1 or a 0. That binary architecture is fast, reliable, and for most problems, more than enough. But there is a category of problems so tangled, so loaded with simultaneous variables, that even the fastest classical supercomputer would need longer than the age of the universe to brute force its way through. Breaking modern encryption, modeling the folding of a single protein, simulating the climate at the level of individual particles. A quantum computer does not solve those problems faster. It solves them differently. Instead of bits, it uses qubits, and qubits exploit 2 genuinely strange properties of the universe. The first is superposition, where a qubit does not have to commit to being a 1 or a 0. It can hold a combination of both states until you measure it. The second is entanglement, where 2 qubits become linked so completely that the state of one instantly influences the other, no matter how far apart they sit. Einstein hated this. He called it spooky action at a distance and spent decades arguing it could not be real. He was wrong, and in 1982, experiments finally proved it. Combine superposition and entanglement across many qubits, and you have built a machine that can explore enormous numbers of possible answers at the same time. For the right kind of problem, that is a different category of fast. It would reshape encryption, artificial intelligence, drug development, and military intelligence at once. That is the prize. And Microsoft thought it had found a shortcut no one else could see. A shortcut that ran straight through the work of the missing Italian. The bet nobody else would make most people think of Microsoft as a software company. Windows, Office, the Excel spreadsheets your boss sends at 11 on a Friday. Fair enough? But for nearly 2 decades, the company has been running one of the most ambitious and least publicly discussed research efforts in the history of computing. It began in earnest in 2003, when Microsoft established Station Q, a research outpost based at the University of California, Santa Barbara. The name reads like a Cold War cable, which I appreciate. Station Q was built around a specific and controversial bet. While Google and IBM chased quantum computing using the most obvious available technology, superconducting circuits, Microsoft refused to follow the pack. The company gambled everything on what most physicists called either visionary or delusional, depending on which side of the lab bench they were standing on. Microsoft committed to the topological qubit. Here is why that mattered. The qubits Google and IBM were building are unbelievably fragile. Heat disturbs them. Vibration disturbs them. Electromagnetic interference disturbs them. Even cosmic rays passing through the Earth can wreck a calculation in progress. The technical term for that collapse is decoherence, and it is the central nightmare of quantum computing. You can build a qubit. Keeping it stable long enough to do anything useful with it is what breaks careers. Current quantum machines have to be cooled colder than deep space, and they still make errors constantly. Topological qubits were supposed to end that nightmare. The ZF theory, developed largely by a mathematician named Alexei Kitaev, whose work Microsoft acquired by essentially hiring him, proposed that you could encode quantum information not in the trembling state of a single particle, but in the topological properties of a whole system. Properties mathematically protected against local disturbances because they depend on the global structure rather than any one fragile detail. In plain language, a topological qubit was supposed to be a qubit you could not knock over by sneezing in the same room. The math was elegant, the framework was beautiful, and it all depended on a particle that had never been confirmed to exist. The particle Ettore Majorana had described in his 1937 paper, the year before he walked up that gangway in Naples. A particle that behaves like nothing in the standard zoology of physics. A particle that is, in a sense, the math takes very seriously. Its own anti-particle. Microsoft would spend 17 years building a research empire on the theory that this particle, predicted by a man who deliberately erased himself from the world, could be coaxed into existence inside a nanoscale device. They assembled the finest condensed matter physicists in the world. They built specialized facilities. They called the topological qubit their secret weapon in the quantum race. In 2017, they announced a breakthrough was imminent. What they did not announce was where most of that breakthrough was actually happening. The building that was not on any tour. Most of Microsoft's publicly acknowledged quantum work happened through Station Q and through partnerships with universities. But Delft University of Technology in the Netherlands quietly became the most important site in the entire program. Delft had the expertise, the fabrication equipment, and the nanoscale capability to actually build the devices topological qubit research required. On paper, it was a normal academic collaboration. In practice, it was something else. Researchers who worked adjacent to the program described protocols that did not belong in a university physics department, access controls more appropriate to a defense contractor, non-disclosure agreements unusual in scope, even by industry standards, findings that traveled through internal channels and bypassed the normal academic disclosure process. Now, I want to be careful here, because a lot of this is simply corporate secrecy, which is mundane and explains plenty on its own. Microsoft is a publicly traded company with billions of dollars riding on getting to a working quantum computer first. Of course, they kept things close. That is Tuesday in Silicon Valley, or in this case, Tuesday in the Netherlands. If you want to know what was actually happening inside that building, hit subscribe. Because what Microsoft has spent 4 years not explaining is next. There is a difference between corporate secrecy and the pattern that surrounded this program. Results were withheld from peer review for unusual stretches of time. Collaborators were told to limit what they shared with their own institutions. And then there was a paper that went through the peer review process at the most prestigious scientific journal on Earth, got published with enormous fanfare, and was then retracted, not because of imprecise language, not because of a sloppy graph, but because the underlying data had been manipulated. If you have been watching this channel for a while, you know I do not throw the word manipulated around lightly. Stick with me, because the way that paper fell apart tells you everything about what was really happening inside that lab. The Nature paper that detonated in 2018, a team of researchers including scientists from Delft and Microsoft published a paper in Nature. Nature is not a minor publication. It is arguably the most prestigious scientific journal on the planet. Getting a paper accepted there is the academic equivalent of winning a championship. Careers are built on a single Nature byline. The peer review process is engineered specifically to catch the kind of problems this paper turned out to contain. The paper claimed to present the first definitive experimental evidence of Majorana fermions in a nanoscale device, the Holy Grail. The ghost the entire program had been chasing for 15 years, finally pinned down in a lab in the Netherlands. The evidence looked clean. The data looked compelling. The theoretical framework lined up. The scientific community was cautiously thrilled. If this was real, Microsoft had just lapped the field before most people knew the race had a finish line. Then other researchers started trying to reproduce the result. They could not. When independent groups attempted to replicate the experimental conditions and the observations described in the paper, the numbers refused to cooperate. Discrepancies appeared between the raw data and the data shown in the publication. Questions about how certain measurements had been processed began circulating in private among theoretical physicists, then in larger groups, then loudly. In 2021, after years of investigation, Nature retracted the paper. Scientific retractions happen. Science is meant to be self-correcting. Papers get pulled because of honest errors, because of methods that turn out to be flawed. That is the system working as designed. But this retraction was different, because the investigation that triggered it did not find an innocent mistake. It found that raw data, the actual numbers coming out of the actual physical experiments, had been selectively processed in ways that made the results appear more conclusive than they were. Data points that contradicted the conclusion had been omitted. The presentation had been shaped to tell a particular story, rather than to honestly reflect what the apparatus was showing. That is not a slip. That is a career-ending finding, and it raises immediate serious questions about what was happening inside that research environment. Why would scientists at the absolute top of their field, publishing in the most prestigious journal on Earth, feel pressure to make their results look better than they actually were? What were they being pushed toward? And here's the question almost nobody in mainstream coverage has been willing to ask. What did the real, unmanipulated data actually show? The quiet departures. After the retraction, something interesting happened. People started talking, not loudly, not at press conferences, but in the corridors of conferences, in private emails that eventually found their way to science journalists, in carefully hedged language that said more in what it refused to mention than in what it confirmed. The picture that emerged was of a program operating under extraordinary pressure. Microsoft had made public commitments about the timeline for quantum breakthroughs. Executives had spoken at conferences. Investors had been briefed. The narrative of topological qubits as Microsoft's secret weapon had been woven into the company's long-term story. And the researchers at the sharp end, the ones expected to deliver on that narrative, were caught between extraordinarily difficult physics and the expectations of a company that had spent 17 years being told it was going to win. Several researchers who had been part of the program left quietly, not with departures that generate press releases, but the kind that happens when someone decides they need to no longer be associated with something. LinkedIn profiles updated. University affiliations changed. Publication records that had been steady suddenly went silent for a year, then resumed in different research areas entirely. One researcher, whose name I will not use because they have never spoken publicly, described in private communications later, reported by science journalists, an environment where negative results were treated as problems to be solved, rather than data to be reported, where the operative question was not what the experiment shows, but how do we get the experiment to show what we need it to show? That is not science. That is engineering a narrative. And it leads to the question mainstream coverage has never asked clearly enough. If the positive results were manufactured, what did the real results look like? Because here's the thing about manipulated data in physics. You do not manipulate data that shows nothing. You manipulate data that shows something real but messy, something that almost works, something that contains a genuine signal buried in complications the researchers did not know how to explain. So the question was never whether the Majorana detection had been overstated. The evidence strongly suggests key parts of it were. The question is what the underlying data was showing. And in the months after the retraction, in late-night phone calls between physicists who had touched the program, and physicists who had only heard about it, that question started circling something none of them wanted to say out loud. What the devices were actually doing. This is where the official story stops, and where I want to be the most precise, because this is exactly the territory where speculation and evidence have to be handled like glass. So let me tell you what we know, what is strongly suggested, and where we cross into informed interpretation. What we know is this. The experiments at Delft were producing results, not the clean, conclusive results presented in the Nature paper, but real signals coming out of real physical systems. The researchers were observing behaviors in their nanoscale devices that did not fit neatly into existing theoretical models. In condensed matter physics, when you build a nanoscale device under extreme conditions, and we are talking about temperatures within fractions of a degree of absolute zero, magnetic fields tuned to extraordinary precision, electrical environments controlled to an almost absurd level of accuracy. And you start seeing anomalous behavior. There are broadly two explanations. Either your setup is generating artifacts that look like physics, or you are seeing real physics your models do not yet have a place for. The Delft experiments were producing what physicists call a zero-bias peak. This is a specific signature in conductance measurements that theory predicted should be a marker of Majorana behavior. The problem was that the zero-bias peaks the team was observing could also be produced by completely conventional mechanisms that had nothing to do with Majorana fermions. Distinguishing between a true topological signal and a mundane quantum effect that mimics it requires extensive cross-validation, multiple independent measurements, and a level of experimental control that pushes the very limits of what current technology can do. But here is what the sanitized version of this story leaves out completely. In certain experimental configurations, the devices were showing behaviors the conventional mimicry explanations could not fully account for either. Not Majoranas as the textbook predicted, not the known alternatives, something else, something the existing theoretical framework did not have a clean home for. There is a moment that has stayed with me from the reporting around this story. A senior theoretical physicist who had consulted with the program, sitting in a small cafe a short walk from the Delft campus, stirring a coffee that had gone cold an hour earlier, finally answered a question a science journalist had been circling for the entire conversation. The physicist did not look up. They had been thinking about this for years, and what came out was not a sentence they had practiced. It was the closest thing to a confession the field has produced. The data was not showing them what they wanted, but it was showing them something, and they did not have the vocabulary yet to describe it. Sit with that for a second. What it suggests is that the program, for all its failures of scientific integrity, was generating genuinely anomalous observations inside physical quantum systems. Observations the current theoretical framework of topological quantum computing cannot fully explain. Observations strange enough and potentially significant enough that the people working with them chose to dress them up rather than admit they could not categorize them. And somewhere between that cafe conversation and the present moment, the program that produced those observations went dark. The lights going out. In late 2021 and through 2022, specific configurations of the Delft research program were quietly wound down. Not all of Microsoft's quantum work, the broader program, kept going, but particular experimental setups, particular research threads, particular collaborations were ended without fanfare, without the kind of public statement you would expect if the program had simply reached a natural conclusion. The official explanation, to the extent there was one, was restructuring, refocusing. The standard language of corporate programs pivoting toward more productive directions. And there is genuine truth in that. After the retraction, the approach that had defined the program's first decade and a half had been publicly discredited. A reset was necessary, but the specific shape of what was shut down, and even more importantly, what was not transferred, written up, or published when it closed, raises questions the word restructuring does not begin to answer. In normal scientific practice, when a research program ends, the data is preserved. The findings are written up. The results enter the scientific record, even if they are negative or inconclusive. Null results have value. Anomalous results have enormous value. Other researchers can build on them. That did not fully happen here. Some data from the closed experimental configurations has never appeared in any published form. Some research directions active in early 2021 simply stopped appearing in any public scientific record after the shutdown, with no published explanation. In 2023, Microsoft announced what they framed as a genuine milestone: topological qubits meeting a specific reliability threshold the company called measurement precision. The claim was published carefully. The retraction had clearly taught them something about presentation. The language was more modest, more hedged, accompanied by an explicit invitation for independent verification. But even this more cautious announcement did not explain the gap, the years between the retracted paper and the new claim. The researchers who left during that window. The experimental setups quietly dismantled and rebuilt. Whatever was inside those rooms in 2021 is not inside the 2023 announcement. And nobody who was there in 2021 is saying where it went. Why this race warps everything it touches. Let me tell you why this matters far beyond one corporate research program. The global race to build a functional quantum computer is one of the most consequential technological competitions in human history, and the stakes are so high, they are already bending the scientific process around them. Modern encryption, the technology that protects your banking, your private messages, your government's classified communications, and essentially the entire architecture of trust on which the digital world runs, is based on mathematical problems classical computers cannot efficiently solve. A sufficiently powerful quantum computer would break most of that encryption almost instantly. Every encrypted message ever recorded could theoretically be decrypted retroactively. Financial systems become vulnerable. Military communications become vulnerable. The advantage of getting there first is so enormous, it registers as a national security issue for every major government on the planet. China has invested an estimated $15 billion in quantum research. The United States has designated quantum computing as critical for national security. The European Union runs its own quantum flagship program. The race is real. The pressure to show results is intense. And that pressure is producing exactly the kind of scientific compromise we saw at Delft. Here is the part that should keep you up at night. That pressure does not just produce bad data. It produces the concealment of genuinely interesting data, because in a race to announce a breakthrough, anomalous results that do not fit the expected narrative are more dangerous to a program than no results at all. An unexplained observation is harder to manage than a clean negative result. So, it gets buried or it gets dressed up as something it is not. Either way, the actual science suffers. What the Delft experiments may have been brushing up against, imperfectly, inside a program distorted by pressure, is a genuinely new regime of physical behavior in quantum systems. A regime where topological protection of quantum states is not the clean theoretical ideal the textbooks describe, but something messier, requiring entirely new frameworks to understand. If that is correct, the most important findings from Microsoft's quantum program are not the ones they announced. They are the ones they could not explain. The questions nobody will answer. Microsoft has said the carefully managed minimum about all of this. They have acknowledged the retraction, they have announced the restructuring, they have continued to publish through their quantum division, and have made what appear to be genuine incremental advances in their more recent research. But there are specific questions Microsoft has never answered, and that journalists covering the quantum beat have not pressed hard enough on. What happened to the raw data from the experimental configurations shut down in 2021 and 2022? Where are the researchers who departed during that window? And why have so many declined to discuss their work there even years later? What specifically triggered the decision to end particular experimental threads rather than continue them in modified form? And what does the unmanipulated data from the Delft devices actually show? The silence around these specific questions is not the normal silence of corporate discretion. It has a particular texture, the texture of people who were present at something significant and have been asked, formally or informally, not to discuss it. Some of the researchers who left have continued publishing in adjacent areas of physics. Their newer work shows clear continuity with the theoretical questions explored at Delft. They are still working on the problem. They are simply not talking about what they found. That is the silence that says everything. What I actually think happened. I have been sitting with this story for a long time, and I want to tell you what I actually think, rather than just laying out the evidence and walking away. That is what we do on this channel. We do not just present mysteries, we try to think through them. Here is my honest read. Microsoft did not discover a fully functional topological qubit inside that facility. The evidence does not support that conclusion, and the retraction makes it impossible to claim credibly. What I believe they discovered was something less cinematic and, in some ways, far more important. They discovered that the boundary between topological quantum behavior and conventional quantum behavior in real physical systems is not where the theory said it was. It is messier, more dependent on specific materials, more dependent on specific experimental conditions, and harder to define than the elegant predictions suggested. If that finding had been published honestly, as a set of anomalous observations requiring new theoretical frameworks, it would have been enormously valuable to the entire field. It would have recalibrated the global research community's understanding of what topological quantum computing actually involves. It would have been less exciting than announcing the capture of the Majorana fermion. It would have been more honest and, in the long run, more useful to every scientist on Earth working on this problem. Instead, the program chose the narrative over the data. When the narrative collapsed, the data went with it. I do not believe there is a cinematic cover-up here. I do not picture Microsoft executives in a dark room deciding to suppress a revolutionary discovery. What I think happened is more ordinary, and in some ways more troubling. A program under enormous pressure, chasing an enormously important goal, found something that did not fit its expected story. And the institutional machinery around the researchers was not built to handle that honestly. So it was handled dishonestly. Then it was shut down. And the interesting thing they found is sitting on a hard drive in a researcher's filing cabinet, not yet integrated into any public scientific record. The quantum race continues. Microsoft is still in it. Their newer results are more careful and may turn out to represent real, durable progress. But the question of what was specifically observed in those Delft devices in the years before the shutdown has never been fully answered, and the scientific community deserves a better answer than the one it has been given. Because here is what we know from every other moment in history where something was observed and then buried. It does not stay buried. Physics is not corporate strategy. The universe does not sign non-disclosure agreements. Whatever was happening inside those quantum devices, at temperatures within a whisper of absolute zero, in a nondescript building in the Netherlands, will eventually be observed again. Probably by someone who is not even looking for it. When it is, we will look back at the Microsoft program not as a story of failure, but as the story of a discovery the people who made it were not equipped to handle. The facility is dark, the researchers have moved on. The official story has been told and mostly accepted. But the physics does not care about any of that. The discovery is still out there, waiting to be made again by someone honest enough to report what the data actually shows. If this story unsettled you, share it with someone who should know, and hit subscribe so you do not miss what is coming next. Because in the next video, I am going inside what China's $15 billion quantum program may already have found that the rest of the world has not been told about. And if you think Microsoft kept secrets, wait until you see what is happening in the labs outside Hefei. I will see you in the next one.